Okay, yeah. Thank you, and thanks to the organizers for putting together this very nice workshop and for inviting me to come and speak. So today I'm going to be talking about some new results concerning graph distances in random planar maps and distances in Liouville quantum gravity for general gamma between 0 and 2. And this will be primarily based on a joint work with Jian Ding, but there's also a number of joint works with other people which will also be relevant who I've listed here. Okay, so okay, this does not. Oh, there we go. So I'm sure you all know what Liouville quantum gravity is, but let me just quickly remind you about a couple of points here. Suppose we have a parameter gamma between 0 and 2 and a domain D in the complex plane. Then heuristically speaking, a Liouville quantum gravity surface is supposed to be something like the random Riemannian surface, whose Riemannian metric tensor is given by like the exponential of the Gaussian free field times the Euclidean metric tensor. Okay, so of course this does not make literal sense, but it's expected that one should be able to define Liouville quantum gravity as a random metric space for all values of gamma between 0 and 2. In other words, we should be able to define on our domain D a random metric which should, in some sense, correspond to exponentiating gamma times the Gaussian free field. Okay, and this metric is expected to describe the scaling limit of random planar maps with respect to the Gromov-Hausdorff distance. So for example, the case when gamma is equal to square root of 8/3 corresponds to uniform planar maps, and then other values of gamma correspond to planar maps weighted by the partition function of some sort of statistical mechanics model. For example, the uniform spanning tree for gamma equal to square root of 2, or bipolar orientations for gamma equal to square root of 4/3. Okay. So far, the only case in which this Liouville quantum gravity metric has actually been constructed is when gamma is equal to square root of 8/3. Okay, so in this case, the metric was constructed in a series of works by Scott and Jason. And this metric has the same topology as the Euclidean metric, but it has Hausdorff dimension 4. So it's a very fractal sort of metric space structure on a domain in the complex plane. Scott and Jason also showed in their construction that this metric is equivalent in the sense of being isometric to a Brownian surface, like the Brownian map or the Brownian disk or what have you, when you take a certain special type of Liouville quantum gravity surface and use it to define your square root of 8/3 LQG metric. So in particular, thanks to work by Legal and Mirmont and others concerning the scaling limits of random planar maps, we know that the scaling limit of uniform random planar maps of various types are given by Brownian surfaces, and therefore we also know that uniform planar maps are converging to this LQG metric in the case when gamma is equal to square root of 8/3. Okay, so to kind of briefly summarize what happens here, we have a pretty good understanding of what happens for graph distances in uniform random planar maps, and also for distances in Liouville quantum gravity in the special case when gamma is equal to square root of 8/3. On the other hand, when gamma is not equal to square root of 8/3, or equivalently when we're looking at planar maps weighted by some sort of statistical mechanics model, we still have a pretty poor understanding of how graph distances are supposed to behave. So in particular, in this case, there's no construction of a metric on Liouville quantum gravity, so we don't have like a candidate for the limit of the graph distance on these weighted random planar map models. And furthermore, we don't even know like what kind of basic properties this conjectural metric should satisfy. So one very natural question to ask about this LQG metric is what its Hausdorff dimension should be. This is the question that I want to primarily focus on today. Okay, so currently we don't know what this dimension is, but there's been a bunch of work in the physics literature, and there's actually been sort of several different predictions which kind of give guesses as to what this dimension should be. So kind of the best known and maybe kind of in some ways the most plausible looking prediction, or actually, yeah, so the most plausible looking prediction was this formula due to Wadowicki in 1993. And he predicted that the dimension of LQG should be given by this formula here. And I guess I forgot to mention this line, which So that, this dimension of LQG is supposed to arise in a bunch of other places in addition to just this conjectural LQG metric. For example, it's supposed to describe the ball volume growth exponent for random planar maps in the LQG universality class. Okay, so at least at a heuristic level, knowing this LQG dimension is like the same as knowing the exponents that govern distances in appropriate types of weighted random planar maps. Okay, so we have this prediction by Wadabiki, but currently it's now known that this prediction is actually false. The reason for this is that there's results by Ding and Goswami from 2016, and what they showed is that for certain discrete approximations of distance, or certain approximations of distances in Liouville quantum gravity, they got an upper bound which is inconsistent with this Wadabiki prediction when gamma is very small. So we know that at least in the regime when gamma is really small, this formula can't possibly be correct. However, it does appear to have some degree of validity. So it gives the right answer when gamma is equal to square root of 8/3, which I guess is good. It's right at the one place where we actually know what the answer is. And it also appears to match up reasonably well with numerical simulations. So for example, there's some works by Ambjorn and Budd where they simulate large random planar maps and other approximations to Liouville quantum gravity distances. They compute exponents for distances, and it appears to match up reasonably well with this Wadabiki prediction here. So I'll say some more a bit later in the talk about kind of what we expect the actual answer to be here once I've discussed the results that we're able to prove. Okay, so let me now move on to the main results that we prove about distances in LQG. Even though we don't actually have a metric on LQG for gamma not equal to square root of 8/3, we're still able to kind of begin to build an understanding of what this metric should look like because we have a bunch of well-defined approximations to distances in LQG, which we can actually analyze in various ways. So, of course, the best known approximation to LQG is just going to be distances in random planar maps. But there are also a number of ways of approximating a Liouville quantum gravity metric by starting from continuum quantities associated with LQG and then trying to build a metric from those. So one option is what's called Liouville graph distance. So what this is it's kind of a way of trying to approximate distances in LQG by using the LQG metric. Okay, so we know that, so basically what you do is you define the distance between 2 points in the complex plane to be the minimum number of Euclidean balls of LQG mass epsilon whose union contains a path between the 2 points. So these balls will typically have very different Euclidean sizes, but they'll all have the same LQG mass. And you just look at like how many of these balls you need to string together to get between your 2 points. And you declare that to be the distance between the 2 points. Okay, so this is one way to approximate LQG distances. Another option is what's called Liouville first passage percolation, or LFPP. And this is based on the idea that LQG is supposed to correspond to, in some sense, like the exponential of the Gaussian free field. So what we can do is we can look at a parameter xi greater than 0, which for reasons which I'll explain momentarily, we're actually going to take to be equal to gamma over d sub gamma, where d sub gamma is the LQG dimension. And then what we do is we just look at the exponential of some family of continuous functions which approximate the GFF. And then we define the distance between 2 points to be the minimum of the exponential of xi times these continuous functions integrated over paths going from z to w. Okay, and for our purposes, we're always going to take this h delta here, so these continuous functions which approximate the GFF, to just be the circle average process, because it's a very nice approximation of the GFF to work with. But we expect that we should have that kind of it shouldn't matter, and you should get sort of the same limiting behavior and the same exponents and so forth if you'd use other approximations of the GFF instead. Okay. And finally, another way of approximating distances in LQG is based on what's called the Liouville heat kernel. So this is the heat kernel for Liouville Brownian motion, which you heard about in Ofer's talk last week. Basically the idea here for like why this should be relevant to distances is that if you take a Liouville Brownian motion and you condition it to go between 2 points in an unusually short amount of time, then it should be approximately following an LQG geodesic between the 2 points. So this kind of suggests that the short-time asymptotics of the Liouville heat kernel should be related to distances in Liouville quantum gravity. Okay. So the main result, so kind of a priori, if we just look at these four different things, they're all defined in very different ways, and it's not really clear that there should be any rigorous connection between them, besides the fact that they're all supposed to be related to distances in LQG. So the first main result that I want to present today is that there's a single exponent, d sub gamma, which describes distances in all four of these different settings. Okay, and furthermore, I'm going to explain how to show that this d sub gamma is increasing in gamma, and how to prove new upper and lower bounds for it, which in most cases substantially improve on previously known bounds for any of these four quantities. Okay, so in some sense, we can think of the theorem as saying that even though we don't have a metric on Liouville quantum gravity, the fractal dimension, or the Hausdorff dimension of LQG, is in some sense well defined, because we can look at all of these different approximations of LQG distances, and they all have sort of a natural notion of dimension associated with them, and the dimension is going to be the same. It's going to depend only on gamma, and it'll be the same for all of these, whatever kind of approximation to distances we want to use. Okay. So let me now say, give a little bit more detail about the results that we prove. Okay. So the starting point of our analysis is actually the paper of Ding, Zaitouni, and Zhang, which Over talked about in his talk last week. And so what they show in their paper is that if we look at Liouville graph distance, then there actually exists an exponent for distances with respect to this approximation. Okay, so there'll be some exponent d sub gamma, such that the typical Liouville graph distance between 2 points z and w is going to be of order epsilon to the negative 1 over d sub gamma. Okay, so like you need of order epsilon to the negative 1 over d sub gamma balls in order to get like a path between two typical points. All right, so this result was proven via a subadditivity argument, and it doesn't really give much information about the actual value of this d sub gamma, but we do know that the exponent exists. And that's going to be kind of the starting point of our analysis. And it was also shown in the same paper by Ding, Zaitouni, Zhang that this exponent d sub gamma here also describes the short-time asymptotics of the Liouville heat kernel. Okay, so this is sort of the way that the other stuff is connected to the Liouville heat kernel. And that's actually all I'm going to say about this object here. For the results that I'm going to prove, I'm just going to use the existence of the Liouville graph distance exponent. Okay. So the next part that I want to talk about is how all of this relates to random planar maps. Okay. So in this context, the main result that we prove is that for a large class of different natural infinite volume random planar map models, including the UIPT, as well as planar maps weighted by the number of spanning trees they admit, mated CRT maps, infinite bipolar-oriented maps, and so forth, the exponent for the volume of a metric ball in the planar map exists, and it's equal to the same exponent d sub gamma, which shows up in Liouville graph distance in the Liouville heat kernel. Okay. So a couple of comments about this result here. So first of all, remember that I said before that like the dimension of LQG is supposed to be related to this ball volume growth exponent, and so this gives kind of strongly suggests that this d sub gamma is supposed to be kind of like the correct value for the dimension of LQG. So it's like the right exponent to be looking at. Furthermore, and a very important consequence of this result for our purposes is that in fact in the case when gamma is equal to square root of 8/3, this exponent here is equal to 4. Okay, so we do get the right value of the exponent when gamma is equal to square root of 8/3. And this is actually kind of not at all obvious in the setting of the Liouville heat kernel or Liouville graph distance. All right, so it's kind of a new result in those contexts, and this fact that d sub square root of 8/3 is equal to 4 in our setting is actually only coming from the planar map connection. Okay, it just comes from the fact that we're able to analyze that distances in the UIPT are well understood, and so because of our results relating exponents, we're able to back out what the exponent is when gamma is equal to square root of 8/3. Okay, and that's going to be a very important ingredient in the proof of our bounds for this exponent here. Okay, so I'm not going to say too much about how this connection to random planar maps is proven, because essentially it's just following the same techniques that Jason talked about in his series of lectures last week. So basically the idea is that for this certain special type of random planar map called the mated CRT map, one can represent the mated CRT map as the adjacency graph of epsilon LQG mass cells, which are defined using space-filling SLE on a Liouville quantum gravity surface. Okay, so you'll have a bunch of kind of chunks of space-filling SLE, which will kind of be fractal in shape, but they'll all have the same LQG mass, and the mated CRT map can be shown to be just the adjacency graph on these chunks. And this comes from the mating of trees theorem by Duplantier, Miller, and Sheffield. All right. Now, one can show that these cells here do not have kind of too wild of a shape. They're kind of roughly spherical in the sense that their squared diameter is typically comparable to their area. So this means that like the mated CRT map admits like a representation which looks very much like Liouville graph distance, right? So like if we take two points Z and W, then the number of cells that you need to get a path from Z to W is going to be basically comparable to the number of balls that you need to get a path from Z to W. Okay, so this allows us to say that distances in the mated CRT map can be related to Liouville graph distances, and that leads to the theorem in the case of the mated CRT map. And then for other planar maps, we use like the strong coupling result for the mated CRT map, and the other planar maps, which Jason discussed a little bit last week. And it's just like the same strong coupling tool, which is used to analyze the random walk on these various random planar maps. Okay. So that's all I want to say about this random planar map theorem for now. And then I want to move on to our main result in the case of Liouville first passage percolation, which recall is the approximation to distances in LQG that you get by exponentiating the circle average of the Gaussian free field. Okay. So here, the main result that we prove is a little bit more complicated looking than some of the other theorems that I've stated. So what we show is that if we take LFPP with exponent xi equal to gamma over d sub gamma, which means that we're exponentiating gamma over d sub gamma times the circle average of the GFF, then the LFPP distance between two fixed points z and w is typically going to be of order delta to the 1 minus 2 over d sub gamma minus gamma squared over 2 d sub gamma. Okay? So where here d sub gamma is this usual exponent, which was defined using Liouville graph distance. Okay. So let me make a couple of comments here on where these exponents, gamma over d sub gamma and 1 minus 2 over d minus gamma squared over 2d actually come from. So you can kind of see why we should have xi equal to gamma over d sub gamma as follows. Now we expect that d sub gamma should be like the dimension of LQG, so it should be like the exponent relating distances and areas. Okay? So if we wanted to scale Liouville quantum LQG areas by a factor of c, then what we need to do is add 1 over gamma log c to our Gaussian free field. Okay? On the other hand, if we take xi equal to gamma over d sub gamma, then adding 1 over gamma log c to the GFF is going to scale LFPP distances by a factor of c to the 1 over d. Okay? So scaling areas by c corresponds to scaling distances by c to the 1 over d, which is what we should expect. And so this is kind of why we have to have xi equal to gamma over d sub gamma here. Okay, and then the source of this exponent for distances is maybe a little bit more subtle, but I will briefly mention here that the exponent is equal to 1 minus xi q, where q is this usual LQG coordinate change constant, and it's related to and the value of this exponent is related to what happens when you spatially scale. So the measure satisfies this LQG coordinate change formula. We expect the distance function to satisfy the same coordinate change formula, and it turns out that in order for that to be the case, you have to have this particular distance exponent here. Okay, so if I have time, I'll discuss in more detail later in the talk exactly where this is, exactly where we're getting this exponent from. Okay, so right, so this kind of completes the discussion of the universality results, which relate the exponents for different models. And I now want to say what we actually prove about this exponent d sub gamma itself. So first of all, we show that d sub gamma is a strictly increasing function of gamma, and it's also continuous. Okay, so the continuity is sort of obvious, but the fact that it's strictly increasing is pretty non-trivial. It's not at all clear from random planar maps or Liouville graph distance or what have you. And but it is kind of the behavior that we would expect from looking at from like the heuristics for Liouville quantum gravity, because we expect that LQG surfaces should in some sense be getting kind of more fractal as gamma increases, right? So the dimension should be an increasing function of gamma, and this is what we see here. Okay, so in addition to this, we also proved some new upper and lower bounds for d sub gamma, which I've stated here. So we get these kind of ugly-looking formulas. So to get an idea of what these bounds actually say, it's a lot nicer to look at graphs. So here is a graph of the upper bound that we get for the dimension of LQG in blue, the lower bound in red, and then the Wadebiki prediction in green. Okay, so a couple of features that I want to point out here. So first of all, the bounds get kind of much tighter when gamma is larger. And there's a very good reason for that, which I'll talk about in just a moment. And furthermore, they match at exactly 1 point, which of course is the case when gamma is equal to square root of 8/3 and d is equal to 4. Okay. And also the other thing that I want to note is that these bounds are still consistent with the Wadebiki prediction. So the Wadebiki, the graph with the Wadebiki curve is between the red and blue curves. Okay, so here's another picture where I've zoomed in just on the interval from square root of 2 to 2, so you can see a little bit better what the bounds look like in this regime. Okay, and as you can see, they're pretty close together. They differ from Wadebiki by about 0.1 on this interval. Okay, so so let me now say a few things about these bounds. So first of all, as we can see from the graphs, we show that d sub gamma is strictly bigger than 4 for any gamma greater than square root of 8/3. Okay, and this is actually noteworthy because there's some works in the physics literature which actually suggest that d sub gamma should be identically equal to 4 on some non-trivial interval. Okay, so this is the first rigorous result to actually disprove these sorts of predictions. Okay, however, the new bounds that we get are still consistent with the Wadebiki prediction. Still, the only contradiction to what only rigorously known contradiction to Wadebiki's prediction is the result of Ding and Goswami, which in our setting says that d sub gamma is bigger than 2 plus omega of gamma to the 4/3 over log gamma inverse, and the limit as gamma goes to 0, whereas Wadebiki says that it should behave like 2 plus gamma squared. Okay, so this is still the only contradiction to Wadebiki. So it's very natural to ask, like, what should actually be the correct formula for d sub gamma. So one option is that Wadebiki's prediction is true on some interval, but when gamma is small, there's kind of a kink in the curve, and Wadebiki's prediction is false for small values of gamma, so as to be consistent with this Ding-Goswami result. Okay, so one disadvantage of this possibility is that it would mean that d sub gamma is not an analytic function of gamma. So I don't know if you believe that it should be analytic, but it's maybe a natural thing to guess. And so so if Wadebiki is true on some interval, then of course it can't be analytic because of this Ding-Goswami thing. Okay, so another reasonable guess for the correct answer is that d sub gamma is given by some other formula, which is not Wadebiki's formula, but which is numerically very close to Wadebiki's formula. So it's still consistent with like the numerical simulations and with our rigorously proven upper and lower bounds. Okay, so one possibility is that d sub gamma is equal to this quadratic function here. Okay. No, this is Ding-Goswami just gives a lower bound. Okay, so this guy is linear, and so in particular it's bigger than the Ding-Goswami lower bound. Okay. So this is one possibility. There's not really any theoretical reason to think that this should be true. The way that I got it is I just sort of picked a quadratic equation which so I just pick a quadratic equation which matches at gamma equals 0 and gamma equals square root of 8/3, and then there's still a degree of freedom, so you just pick it to make the function look as nice as possible. Okay, so prior to last week I thought there's no way this is actually right, but last week I actually talked to Timothy Budd and looked at some of the simulations that he's done, and it actually turns out that maybe this formula actually has some validity to it. So if you just look at Liouville graph distance or random planar maps, then you really can't distinguish between these two things. They're just numerically extremely close together, so you can do simulations, and maybe the simulations look like they match a little bit better with the quadratic formula than they do with the Wadowicki formula. For example, like in this figure here, this is the distance between, so this is like the difference between d sub gamma and the Wadowicki prediction. And as you can see, like in the case when gamma is equal to square root of 2, at least the bounds seem to match up better with this quadratic prediction than they do with the Wadowicki prediction. Okay, but on the other hand, if we look instead at LFPP, which because of our formula for LFPP exponents, we see that this quadratic prediction is equivalent to the LFPP distance exponent being equal to xi over square root of 6. Okay, and then on the other hand, Wadowicki says that the LFPP distance exponent should be xi squared. Okay, so here you really actually can see the difference between these predictions. So one can do some simulations of LFPP, and Timothy Budd very kindly has done some such simulations. And so here's like a preliminary graph of what one gets by doing this. And the black dots correspond to like simulated values of the distance exponent. So it looks from this like it's very much preferring this quadratic prediction over the Wadowicki prediction. So maybe this is actually right. I don't know. It's
show that formula one more time. U plus gamma squared over 2 plus gamma over root 6.
Yeah, so currently there's still no theoretical backing behind this thing, but it seems to fit pretty well with numerics, so I don't know. It's still unclear at this point. Okay.
The square root of 6 is canonical once you fix the 2 points, right? Pass it through.
Right, so if you fix the 2 points, then you have three coefficients here in your quadratic equation. So you have 1 degree of freedom once you require it to pass through through 0, 2, and square root of 8/3, 4.
It might be close to 1 over square root of 6, but not exactly square root of 6.
Well, if this is not square root of 6, then the coefficient on this would have to be something other than a half. But if you match those appropriately, then you can get other quadratic predictions which are also pretty close. But I think this is the only quadratic formula that you can get for d sub gamma, which makes the LFPP exponent linear, which is maybe one reason to prefer this over other things. Okay. Right, so that's the current status of trying to guess what the dimension actually is. So I now want to say a little bit about how we actually prove our results. Okay. Or actually, first, sorry, I forgot I had this slide. I first want to say that d sub gamma is relevant to a bunch of other things besides just distances in LQG. For example, as Jason talked about last week, it's possible to show that if we take certain infinite volume random planar maps, like the same ones that we proved the ball volume growth exponent for, then one can show that the distance traveled by a simple random walk in the planar map after n steps is typically going to be of order 1 over d sub gamma. Okay, so like the ball volume growth exponent for random planar maps is the reciprocal of the random walk growth exponent. Okay, so in particular, this says that random walk on all of these random planar maps is subdiffusive with reasonably nice bounds on the subdiffusivity exponent. Okay, and the other thing that I want to mention, which you'll hear more about from Josh Pfeffer tomorrow, is that our results are also relevant to the study of external DLA on span and tree weighted planar maps. So in particular, if we take a span and tree weighted planar map and we look at external DLA on it, and grow our cluster for n steps, so we have like n particles coming in from infinity, then the graph distance diameter of the DLA cluster is going to be of order n to the 2 over d sub square root of 2, where d sub square root of 2 is this LQG dimension exponent for gamma equals square root of 2. So I won't say anything more about that because this will be the topic of Josh's talk tomorrow. All right, so now I want to move on to the proofs of our results. And I'll start by discussing the proof of the monotonicity and bounds for d sub gamma. Okay, so the basic idea of where our upper and lower bounds come from is that we want to combine the results that we have for different models. So we're very much going to be exploiting the relationships between exponents, and it kind of turns out that once one combines things for a bunch of different models, which are kind of essentially obvious from the individual models, then one kind of magically gets these very nice upper and lower bounds for d sub gamma. So let me now explain how this works. So there's kind of going to be two key inputs that we need to get our bounds. So the first one is, as I mentioned earlier, from the planar map connection, we get that when gamma is equal to square root of 8/3, our exponent is equal to 4. Okay? And then the other statement that we need to get our bounds is a certain monotonicity statement for various functions of gamma and d sub gamma, which I claim comes from LFPP. So I'll explain where this monotonicity comes from in just a moment. But once we know that these two functions are increasing in gamma, then we immediately get the desired upper and lower bounds for d sub gamma in the following way. So for example, let's say we wanted to prove an upper bound for d sub gamma in the regime when gamma is greater than or equal to square root of 8/3. Okay? Well, we know that when gamma is greater than or equal to square root of 8/3, because this guy is increasing and d sub square root of 8/3 is equal to 4, then we know that gamma over d sub gamma is greater than or equal to square root of 8/3 over 4. Okay? And then we just rearrange and we get d sub gamma is less than or equal to gamma times square root of 6, which is the upper bound that we get in the regime when gamma is bigger than square root of 8/3. And then similarly, using like the monotonicity of this thing as well, we get a lower bound when gamma is bigger than square root of 8/3, and in the same way we get lower bounds when gamma is less than or equal to square root of 8/3. Okay. And the bounds that we get when are not optimal when gamma is small. It turns out that when gamma is small, bounds that we proved in a previous paper with Nina and Shin on in the case of the mated CRT map turn out to be better. And this is the reason why we have the kinks in the graphs of our bounds here. Okay, because when gamma is small, we want to use these other bounds that we got for the mated CRT map using completely different techniques instead of the ones that come from monotonicity. All right, so that's how we get the upper and lower bounds. And then the monotonicity of our exponent d sub gamma is essentially an immediate consequence of the monotonicity of this guy. One way to see it, at least heuristically, is you just take an implicit derivative of this thing, then you solve for d sub gamma prime, then you find that d sub gamma prime is positive. But of course, we don't know it's differentiable, so you have to do something a little bit different, but it's just essentially that. Okay, so that's how we prove our monotonicity in bounds. And then the remaining ingredient is I need to explain to you why we know that gamma over d sub gamma and also this function here are increasing in gamma. Okay. So the monotonicity of these guys is going to come from the following monotonicity statement for LFPP. So essentially what we show is that if we look at LFPP with exponent xi, and we rescale it by delta to the xi squared over 2, and then we look at the expected rescaled LFPP distance between 2 points, then up to a delta independent constant, that expectation is going to be like a decreasing function of xi. Okay? So I'll give the proof of this in just a moment. It takes one slide. But once we have this, well, we know that the LFPP distance when xi is equal to gamma over d sub gamma is going to be of order delta to the 1 minus 2 over d sub gamma minus gamma squared over 2 d sub gamma. So if we combine this statement with this monotonicity statement for LFPP here, then we get that whenever gamma over d sub gamma is less than or equal to gamma tilde over d sub gamma tilde, then we also have this inequality here, right? That's just essentially taking this and plugging in the known exponents for LFPP. Okay. And then furthermore, we also know that these two things are equal to each other whenever gamma over d sub gamma is equal to gamma tilde over d sub gamma tilde. Okay. And then so this statement here is going to tell us that gamma over d sub gamma is an injective function of gamma, right? Because if we knew these two things were equal and these two things were equal, then we could rearrange things and get that gamma is equal to gamma tilde. Okay, so gamma over d sub gamma is injective, and therefore it has to be increasing because it's not too hard to see that it's continuous. And so we get this is increasing, and then from this we also get that this guy is increasing. Okay, so that gives us the desired monotonicity. And then all that's left to do is prove this proposition here. Okay, and I claim that this proposition is essentially trivial. Okay, so to prove this, we're going to take a GFF-H. Then we're going to look at another GFF-H prime, which is independent from H and has the same law as H. And then we're going to look at this GFF-H tilde, which is given by this linear combination of H and H prime, and which has the same law as H, as can be seen by computing the variance. Okay. And I'm going to compare LFPP distances with respect to H with exponent xi to LFPP distances with respect to H tilde with exponent xi tilde. Okay? So to do that, I'll start out by looking at like an approximate LFPP geodesic for my field H. Okay, so this is going to be a path which I can assume has the Euclidean unit speed parameterization, over which the integral of e to the xi h sub delta is kind of close to minimal. Okay, and then in order to get an upper bound for the h tilde LFPP distance with exponent xi tilde, I want to integrate e to the xi tilde h tilde sub delta over this same path. Okay, so I'm going to take this integral and look at conditional expectation given h. All right. Now, we remember that h tilde was defined in this way. It's this linear combination of h and h prime. So I can just pass this conditional expectation under the integral sign. The h term is just going to give me an e to the xi h sub delta, and then the h prime term is going to give me this e to the square root xi tilde squared minus xi squared times h sub delta prime. Okay. Now, by basic properties of the circle average process, we know that this h sub delta prime is going to be Gaussian with variance of order log delta inverse. Okay. So this expectation is just going to be given by like so whenever you have a Gaussian random variable, a centered Gaussian random variable, you want to look at the expectation of like e to this random variable, then it's just going to be like the exponential of the variance over 2. Okay. So we just get this factor of delta to the xi tilde squared minus xi squared over 2, and then we get the length of the path, which is just a constant times the LFPP distance from z to w. Okay. And then we can just rearrange this and take an unconditional expectation, and we end up with the desired inequality. Okay. So this gives this kind of completes the proof of the monotonicity of d sub gamma as well as the bounds. Yes. So I'm just trying to get I'm trying to get an upper bound for the xi tilde LFPP distance. So I just need to produce one path over which I can bound the integral, because of course if I have one path over which I have an right. So I'm starting with a path which is close to the infimum.
Start with the path
yes.
on the right. Okay.
Right, because I'm trying to bound the left side in terms of the right side. So I start with something which is close to the infimum on the right side, and then okay. All right, all good? All right, how much time do I have left?
Let's see, you started at
Yeah, I started at 1:45, so I think I've got
1:45. You have an hour.
I thought I had 45 minutes. Okay, anyways, I have at least 10 minutes left. Greater than or equal to 10 minutes. Okay, so I will
maybe it was 45. So.
Okay, so then I will say a little bit about how we relate Liouville graph distance to Liouville first passage percolation. Okay. To do this, I'm going to fix a small parameter beta, which needs to be smaller than 1 over 2 plus gamma squared over 2 for various technical reasons. And then I'm going to compare Liouville first passage percolation with where I'm looking at like the circle average over circles of radius epsilon to the beta. And I'm going to compare this to Liouville graph distance when I'm looking at disks of mass epsilon. Okay? So we're going to compare these two things. I'm going to get the desired relation for the distance exponents for them. Okay, so to do this, I'm going to start out by considering an approximate LFPP geodesic between two fixed points. Okay, so I get this path here, and this path is defined in such a way that like the integral of e to the gamma over d sub gamma times the circle average over circles of radius epsilon to the beta is close to minimal. Okay. So I'm going to look at this path, and now I want to use it to construct like a path of circles between the two fixed points, where the quantum mass of the regions enclosed by the circles is going to be of order epsilon. Okay, so to do that, I start by kind of covering my path by Euclidean squares of side length epsilon to the beta. All right, and now I'm going to look at what happens in each of these Euclidean squares. Okay, so let's look at this Euclidean square in blue. So I have this one Euclidean square, and I want to bound like the Liouville graph distance between the two sides of the squares. Okay, and then I'm going to like sum over all of the squares and use the triangle inequality to get my desired upper bound for Liouville graph distance. Okay, so if I have epsilon Liouville graph distance over in this little square here, then by like basic scaling properties for the LQG measure, I find that the epsilon Liouville graph distance in this little square here is the same as the t epsilon Liouville graph distance in the big square where here t is equal to the exponential of gamma times the circle average over the center of the square times times epsilon to the negative beta times 2 plus gamma squared over 2. Okay? This is just like from the fact that when you add a function to the field, you scale measures by like the exponential of the function, and then plus the fact that you have like this coordinate change formula for the LQG measure. Okay, so we have this this relation between Liouville graph distances in the two squares. And now we know that this 1 over d sub gamma is like the distance exponent for Liouville graph distance. Okay, so we want to look at the t epsilon Liouville graph distance between the two sides of the big square. Well, that's just going to be t epsilon to the negative 1 over d sub gamma, right? And that's just going to be equal to this quantity here. Okay, and I want to emphasize, by the way, that this is where the gamma over d sub gamma comes from, right? Because I had like an e to the gamma h sub epsilon to the beta, and now I take the 1 over d sub gamma power of it, and I get gamma over d sub gamma times h sub epsilon to the beta. Okay, so this is going to be like the Liouville graph distance across one of these squares, and I get the same bound in all of these different squares that I took in the covering of the path. And now I'm just going to sum over all of the squares in the path in order to get an upper bound for the Liouville graph distance between the endpoints. Okay, so right, I sum over all of the squares, and when I do that, I'm going to get a sum of e to the gamma over d sub gamma times like this circle average process, and this is going to be basically like epsilon to the negative beta times the LFPP distance between x and y. Okay. And I just rearrange this inequality here, and I get the desired lower bound for LFPP distances. Then I can do a very similar argument to get the desired upper bound for LFPP distances, and then that kind of concludes the proof of the relationship between LFPP and Liouville graph distance. I want to emphasize here, by the way, that there were lots of technicalities that I glossed over in this proof. You actually have to have, at one point in the argument, one needs to transfer bounds for point-to-point distances, for bounds to bounds for diameters, so we can bound like the diameters of the little squares instead of just the distance between the two sides. But you know, that can all be dealt with, and we do get this this desired relation. Okay. So now, just to kind of briefly summarize, we showed that Liouville. It's now known that like the exponents for distances in Liouville graph distance can be related to exponents for distances in Liouville first passage percolation and random planar maps, and also the Liouville heat kernel, because you know, like our work combined with the work of Ding, Zaituni, Zhang now shows that sort of all four of these things have, you know, sort of the same exponents for distances. Okay, and then using the results for LFPP and random planar maps, we're able to get the monotonicity of the LFPP of the Liouville graph LQG dimension exponent, which was not previously known, as well as some new upper and lower bounds for this guy. Okay, and then I just want to conclude by briefly discussing some open problems. So, of course, the most obvious open problem related to our work is to actually compute this exponent for any value of gamma besides 0 and square root of 8/3, which are the two cases in which it's known. Okay, in particular, can one show, you know, either that the Wadabi prediction holds, or that this alternative quadratic formula holds, or is it, you know, something completely different? And then, you know, maybe as a little side bonus, if you can compute this exponent for any fixed value of gamma, then because of our monotonicity relations, you'll also get new bounds for the same exponent for some non-trivial interval of gamma values. Okay. So that's one question, and currently I don't really have any good ideas for how to get this, but I think it would be, you know, very interesting to know, of course. And another natural question which comes up is to try to find additional mating of trees bijections for random planar maps. Because I didn't really emphasize this, but it was a main point in Jason's talks last week, that you know, all of the results that we're able to prove for random planar maps rely on having like a mating of trees type bijection for the planar map. Like, this is why I was always talking about the UIPT and not the UIPQ, for example, because there's a mating of trees bijection for the UIPT. So it would be of a lot of interest to have, you know, these kinds of bijections for additional planar map models, so we can extend our results to a wider class of random planar maps. Another very natural question which comes out of our work is the following. So remember that we were able to relate LFPP with xi equal to gamma over d sub gamma to Liouville graph distance and random planar maps and so forth. Okay, but this doesn't cover the full range of possible xi values. In particular, our results don't say anything about what happens when xi is bigger than 2 over d sub 2. Okay, in particular, it's very interesting to understand like how distances behave when xi is large. For example, one natural question is like what happens when we send xi to infinity? How does like the LFPP distance exponent behave when we take this limit? And I won't say too much about this here, but this is actually, there's some results that suggest this should be related to Liouville quantum gravity with central charge bigger than 1. So maybe there's some physical motivation for understanding this regime as well. Okay, and then finally, in addition to just this Hausdorff dimension of LQG, there's several other dimensions associated with Liouville quantum gravity, which would be very interesting to know. So one thing that we can look at is the quantum dimension of a connected component of a metric ball boundary. Okay, so typically if we look at like a metric ball in an LQG surface or in a random planar map or what have you, the metric ball is not going to be simply connected. It's going to have a bunch of little holes in it. Okay, so the question is, let's look at the boundary of one of these holes, say the one that's on the boundary of the unbounded connected component. And we want to ask, like, what is the quantum dimension of this thing? Or alternatively, in the planar map setting, if we have a graph distance ball of radius r, then like how many vertices are typically in the boundary of this, like the outer boundary of this metric ball? Okay, so in the case when gamma is equal to square root of 8/3, we know that this quantum dimension is 2. So if you have a metric ball of radius r, then it's going to be of order r squared vertices in its boundary. For general gamma, we don't know what this exponent should be, and it actually appears to be pretty closely related to the Hausdorff dimension exponent. In particular, it seems like the Wadowicki prediction should, at a very heuristic level, be related to the guess that the perimeter of the component should be of order like r to the d sub gamma over 2. Okay, so if you can show that like this is not r to the d sub gamma over 2, then that would be maybe some evidence against Wadowicki's prediction. Okay, so that's one natural question to ask. Another interesting question is to try to understand the Euclidean dimension of Liouville quantum gravity geodesics. Okay, so in this case, unlike all of the other exponents that I've talked about, we don't actually know the answer when gamma is equal to square root of 8/3. We don't even have a guess, even in this case. And really, like one of the only rigorous results that's known in this direction is a paper by Ding and Zhang, which shows that like the Euclidean dimension of LQG geodesics in the setting of Liouville first passage percolation is strictly bigger than 1 for small gamma. So there is like some non-trivial exponent here. Okay, so I guess that's all I want to say. So thank you very much.
Any questions?
Yes?
If I remember correctly, in the Jason and Scott's paper QLE, you had a verification, a heuristic verification. If something was correct in QLE, you recover Wadowicki's formula, and so.
So they said that Wadowicki was true if you explore the metric ball up to some time,
yes,
and then you look at the ball, what is left outside.
yes.
If what is left outside has the same kind of boundary exponents as the quantum disk, it's a regular disk, which is something that we know is true in the root 8/3 case. The outside is just a disk. So if somehow it had the same fractal exponents near the boundary, then Wadowicki would be true.
So you don't believe in that anymore?
But we didn't have any reason to think that it would be the same because you don't have the independence of the outside and what's come. So it would only have to be if it were true by some weird miracle.
Right, and this is related to this this assumption that the outside is like a quantum disk is very closely related to this this ball volume, this outer boundary of the metric ball having exponent d sub gamma over 2. So that's sort of where this is coming from.
Question? Yeah, Nicolas?
So another one. So once you have the exponent, could you push your technique further to get you divide by the expectation and you get tightness? Or there is no hope for
So in the case of LFPP, it's actually known that you have tightness when you divide by the expectation for very small values of gamma. This was done by Ding and Dunlap. And maybe their techniques could be extended to get the tightness for larger values of gamma.
Yeah, but then with your strong coupling, you...
So strong coupling is not good enough to get tightness for random planar maps because it's always going to give you polylogarithmic errors. So this tightness thing would just be for LFPP, and maybe you could extend it to the mated CRT map, but not to like spanning tree weighted planar maps and so forth.
Okay, so let's thank Ewain again.